Hello everyone. So again, welcome back to the latest lecture session. So as is customary, let us have a quick recap of what we have been up to, right? So we have been looking at, I believe, risk assessment, right? In that context, we looked at, I believe, two approaches, one being the deterministic approach and the other being the stochastic approach, right? And we did look at a couple of examples in the case of deterministic approach, and I believe the primary issue or bone of contention between what is it now, this particular deterministic and the stochastic approaches is the use of point estimates in the former approach, and treating variables as variables with mean and spread or variation in this particular context of, or in the context of the stochastic approach, right? So once we were done with that, we did try to understand what are the issues with both these particular approaches. As in the former or in the deterministic approach, right, we are using point estimates to obviously try to estimate a variable, right? So for example, body weight, I think the example we looked at considered an average or mean body weight of 70 kgs, but we do know that the body weights of the relevant affected population can vary widely, right? And also exposure concentrations and so on. So the risk that we end up, or risk I guess, right, that we end up calculating might not be conveying the right information to the relevant management and such, right? So to take that variation or inherent variation within each of these variables into account, we come up with, or we looked at stochastic approach. Yes, in that context we went ahead and started looking at a particular example. So in this context though, obviously the key is that we need a lot more data, right? So you need to be able to get an idea about or estimate the population mean and what do we say, standard deviation, right? And in that context we do know that obviously the sample size is an issue, and thus the bigger the sample size, obviously, right, the closer you will be to the true population mean and standard deviation. So here again we are trying to estimate the mean and standard deviation of the population by analyzing the sample I guess, right? So again in this context we looked at a particular example, I believe, and we went through. So let's look at what we have here. So we are trying to get a histogram, right, showing the distribution of carcinogenic risk. Yes, the key is that it's carcinogenic risk, and here it's the pathway being ingestion of benzene in groundwater. That was the pathway, and we looked at various aspects, but the key was we were trying to calculate the probability of exceeding 10 power minus 6 risk, right? So again, how did we approach this particular problem, or how do we go about analyzing these particular kinds of scenarios, right? We look at or consider the Monte Carlo approach, right? So for each of these particular variables we generate random numbers, right, that would conform to the particular mean and standard deviation and the relevant distribution, I guess. So here in our context I think we had a couple of variables distributed normally, and then a couple of variables distributed log normally, right? So log normally, what was the case in that case? For example, x, if we say that it's log normally distributed, as in these are the data points, what does that mean? So natural logarithm of x, if I take natural logarithm of x and plot that, that will be, or those values will be normally distributed, I guess, right? So and then we consider x to be log normally distributed. So obviously we looked at those cases and went ahead with the relevant analysis, and in that context we also had what we say, or consider the variation in some of the relevant what do we say, parameters such as body weight and slope factor. Yes, so in this case obviously we had one with which is normally distributed and the other which is log normally distributed, right? So in that context we also looked at the example in greater detail. So let's see what we have here. So in Monte Carlo approach, what do we do obviously, or what are we considering, I guess? So we generated, let's say, a considerable set of data set that conforms to the particular distribution, right? So for ingestion of water, body weight, and then log values of benzene in water, because obviously we had it to be log normally distributed. Again, when we consider log normal distribution, it's a natural logarithm, please keep that in mind, right? And from that context we came up with benzene concentration in water. Similarly, I think 10,000 what do we say, random numbers for different such variables, right? So once we calculated intake, right, again 10,000 such what do we say, numbers or data set, let's say, we end up then using that particular intake and the relevant slope factor to calculate the risk, right? So again, what is the key aspect here, or maybe a take home message here? We are trying to replicate all the feasible or different permutations and combinations that can be feasible within these data sets, let's say, or with between these variables in the on the ground. And I think one example I have been repeating is about a person with greater body weight being exposed to lower concentration, a person with lower body weight being exposed to higher concentration, and thus the risks associated are going to be different, right? And obviously you need to be able to capture all those particular combinations, right? So obviously the greater the data set, you know, the closer you will be to the true, what do we say, case out there, right? And you will get a smoother, what do we say, distribution curve or distribution function here, right? So in that context, we went ahead and calculated the risk, right? So we had the particular risk to be calculated here, and you see the different sets of data or risks here for risk, and then we end up plotting the risk. But at a preliminary examination, we saw that it did not make much sense. But the key was that, you know, looks like after we understood how Excel comes up with, you know, the built-in function for histogram, I guess we used the built-in function for histogram to develop the histogram and asked it to automatically calculate the bin size, right? So there are two options here. We could have given the bin range, but we did not do that. We asked Excel or requested Excel to, what do we say, come up with the histogram, let's say, and automatically come up with the bin size. So in that context, let's say, it looks like all the particular risk values were within a particular narrow range. That's how they were distributed, I guess. And with that bin size, looked like there was a skew to the left with all of them bunched together and a particular bin, right? But obviously, you know, I could have changed the bin size and such, but from preliminary understanding, we see that it was, it would follow a log normal distribution, right? So to try to, you know, visualize that, we then took the natural logarithm of risk, and that's out here in this column, right? And then we sorted them out to remove some of these non-numeric values, right? And then we plotted the histogram, and now we see that it's normally distributed. So we have a log normal distribution, and then we have this particular cumulative, what do we say, distribution to here, I guess, cumulative percentage, pardon me, and that's what we see out here. So again, what does this tell me here? Let's see. So bin size, you know, range from -15 to -14, -14.9 to -14.09, and so on. So this will give me an idea about, let's say, the risk that would fall within -12.39 and -11.53. So the area under this particular curve or the frequency, I guess, right? So again, we have on the x-axis the bin size, which in this context is the relevant risk or the natural logarithm of risk, right? So let's try to understand this in the context of what we have been trying to look at. So if we can go back to the particular question, we were trying to understand what is the probability of exceeding 10 power minus 6 risk, right? So let's try to understand that here. So here we are looking at 10 power minus 6 risk. So let me see what its natural logarithm is going to be, is equal to the natural logarithm of, right, 10 to the power of minus 6, right, and I am going to say enter. So looks like I end up with a value of minus 13.81, right. So here the question was asking us to look at, or obviously, you know, the scenario is we are trying to understand what are the chances of this particular exposed population having an additional risk of, you know, contracting cancer, right. And typically, as we know, we look at 1 in a million or 10 power minus 6 chance, right. And in that context, because we are looking at the logarithmic risk here, because it's a log normal distribution, we took the natural logarithm of 10 power minus 6, and the value that I end up with is minus 13.8. So if I look at that out here in this particular graph, that would fall somewhere out here, I guess, right. So that would be somewhere out here, right. So if I do consider this as a distribution function, you know, which I can, let's say, the more I get the data, you know, the closer it would be, I guess. So if minus 13.8, right, which is corresponds to 10 power minus 6 risk falls out here, and what are we trying to get at? The probability that it as in the risk would be greater than 10 power minus 6. But when you try to look at this graph, right, what do you see? You see that almost all the particular data that we have, or the area under this particular graph, is greater than this particular minus 13.8 out here, right. So what does that tell us, right? In this context, it tells us that almost all the people that are exposed to the relevant, you know, this particular scenario, let's say, are going to have, or greater than 1 in 10 power 1 in a million or 10 power minus 6 risk of contracting cancer, right? So that's what we understand from here. Obviously, we can look at the exact value, as in I can plug this in and look at that, or obviously because we already ordered this, again this is also log risk, column M is also log risk. We ordered this I think according to its increasing order or decreasing order. So let me try to sort it in a different manner, right? So okay. So as we see, I try to sort it from an increasing order, and so here if I am trying to look at the number of cases that have a risk of less than 10 power minus 6, so minus 13.8, so I have only 2 cases out of 9,995 cases which we looked at, I guess, right, 10,000 minus those 5 non-numeric values. So the risk of contracting this particular cancer from this particular scenario, what is that, I guess? So here we have 2 cases, only 2 cases out of 9,995, let us say, that would lead to a case or scenario where the risk is less than 10 power minus 6, or 9,993 times out of 9,995 times the risk is greater than 10 power minus 6. Again, that is something we saw from the distribution too, right? I mean, we had something like this, 10 power minus 6 was somewhere out here. So if I want to get the risk greater than 10 power minus 6, so obviously it is going to be all this particular region or portion. As you see, that is almost equal to 1, right? So the probability of the person in this, of any person rather, in this particular scenario, let us say, exposed to those conditions, right, say, right, having an additional chance of contracting risk when we consider 10 power minus 6 risk anyway, is almost 1, right. So there is almost a 100% guarantee that the people there are going to be are exposed to or contract cancer, right, pardon me, considering all the variations that we have taken into account. So obviously you see here that it's a much better approach compared to the deterministic approach, yes. So again, let's say if I wanted to look at a particular any other value of risk, let's say maybe 10 power minus 4 greater than 10 power minus 4, and then I can convey that particular data to the management too. For example, I mean, consider this hypothetical scenario, let's say, as an when the management considers that, okay, 10 power minus 6, we do not have the relevant resources to bring down the risk to that particular value. Maybe I am going to look at, let's say, a 10 power minus 4 threshold for the risk, let's say, a hypothetical aspect. So how would they go about that? Obviously, they will look at 10 power minus 4, let's say maybe here or here, let's say, and look at what are the chances or probability of contracting risk, let's say. So here if 10 power minus 6 is out here, let's say I am just drawing an inaccurate estimate here obviously. So 10 power minus 4, so this would be the probability of contracting cancer, right, if we look at or consider the case of 10 power minus 4 risk. So again, this particular histogram and such stochastic analysis would convey the information in a much better manner, and obviously whenever you can or whenever you can spare the resources to get the level of data required for stochastic approach, stochastic approach obviously is a better approach. For example, if I replace this particular information of the risk and such, right, say, and the relevant distribution with just its mean value, let's say, right. So obviously let us say maybe the mean would be somewhere out here, let us say, but that obviously would not convey the right information regarding the spread of the particular risk associated with this particular scenario, right. So in that context again we are going to wrap up this particular case as in trying to understand in which cases is deterministic approach feasible. Obviously let us say time and resources and also data, and also we looked at or in which cases stochastic approach is relatively better, right. So in that context we are going to wrap up risk assessment, and we are going to move on to the next topic, let us say, as in laws and regulations associated with hazardous waste and their treatment or disposal in our particular country. So in that context we looked at a particular set of rules, right, hazardous and other waste, I think transboundary and movement rules of 2016. So let us move back to that particular case here. So I have that here. So again published in the Gazette of India, right, and we looked at this and how does that, or how did we come about to this particular stage. Let us say as in initially the draft rules, let us say, were published in 2015, they say July 2015. Comments are asked from various sections, let us say industry and public and such. They are taken into account, and then, right, by the powers vested in powers conferred by section 6, 8 and 25 of Environment Protection Act of 1986, they replaced the 2008 or rules with the 2016 rules. And what are the rules that we are typically concerned with right now? Hazardous and other waste management and transboundary movement rules of 2016, right. So in general, let us say you are in industry and you are concerned with, or you operate in industry, let us say, and you are concerned if your particular wastes are, what do we say, probably toxic waste or such, let us say, or hazardous waste, let us say. How do you go about understanding whether your particular industry is generating hazardous waste or such in the first context? So obviously you can look at the information that we are going to consider in this particular case. And secondly, let us say if a site is contaminated, let us say, as we do understand the what do we say, poison lies in the dose, right, and also we looked at the risk assessment and such too. But obviously how can I classify that as a hazardous waste, because there are two classes, one is the municipal solid waste and the other being the hazardous waste in this particular context. So there are different disposal regulations and transport regulations and such for and also handling regulations for hazardous waste. So how do I know whether a particular waste is hazardous, let us say, right? In that context we have a few tests that need to be conducted to be able to understand or classify if a test is hazardous or not. So let us look at what that is about. I think we did look at that briefly, right. So list of here we have schedule 2, okay, and here we have list of waste constituents and their concentration limits. And how do we classify them, I guess, or how do we look at this particular case of understanding whether a particular waste is hazardous or not? We have this particular test based on the leachate concentration limits from the TCLP or the soluble threshold limit concentration, I guess. So typically TCLP. So let us understand or try to look at what this TCLP test is about. So before we go further, what does this say? So you are going to conduct this TCLP test on that particular waste, and after analyzing the relevant concentrations of different compounds as you see here that are listed here, let us say in that leachate, right, you are going to analyze the leachate from that after that particular test, and if the concentration of any of the constituents listed in this particular table here or in schedule 2, I guess, right, and schedule 2 is higher than the concentrations given here, then you would classify that particular waste as hazardous waste. Obviously there are different other classifications too, but this is the primary one typically with which most of the industries are concerned with. Other than that, obviously based on the characteristics, let us say, we also can or do classify a particular waste as hazardous. Primarily flammability, corrosivity, right, reactivity or explosivity, toxicity, right, say. And typically though though we do have this information, we typically go for TCLP tests, and then we have some other aspects regarding their reactivity and such, I guess. Again, they are listed, but typically during the course of our class we are going to be or our course, pardon me, we are going to be concerned with looking at the TCLP test, I guess, right. So again, what is this TCLP test about? So here we have the relevant information corresponding to our particular schedule A, right. So we have different compounds and the limits of what we are going to of that particular compound in the leachate after TCLP test, right. So and here we have our particular TCLP related information. So how do we, or what is this test about? Obviously extraction of, it is concerned with extraction of leachable constituents, and it is the US EPA test method 1311, I guess. So we are going to look at that, and obviously there is another more stringent test which is called the waste extraction test, and that is developed by or available from California Code of or in the California Code of Regulations, I guess, right. But typically we look at the TCLP test. So let us try to understand what that is about, okay. So we are moving on here. So TCLP test, right. So in which context are we trying to look at this particular aspect? We are trying to understand, let's say, if a particular waste, let's say, or contaminated soil, let's say, an example here, can be treated or should be considered as hazardous waste. For example, let's say this is my soil out here, and somebody dropped some chromium, let's say, okay, chromium in this particular soil, okay, and I have chromium in this particular soil, let's say. How do I know if the particular soil can be deemed, this particular contaminated soil anyway, can be deemed to be hazardous waste or not? For that, obviously, I need to conduct the TCLP test, right. So here I gave one example, but let's try to look at the background for this TCLP test. So what happens to the waste if you do not consider it to be hazardous waste, right? It would end up in a municipal solid waste landfill, right? Typically anyway, if not in this example of contaminated soil, typically let's say if there is an issue with, or you need to make a call regarding a particular waste, if it's hazardous or not, and if you come up with the relevant or take the call that it's not hazardous waste, where will that waste end up in? Let's say in a municipal solid waste landfill. And what conditions prevail in this municipal solid waste landfills now, or in this municipal landfills? You have acidic conditions from the anaerobic degradation, as in, let's say, over time, okay, assuming that this is the liner, okay, and the relevant leachate collection system and so on, semi-impermeable layer and such. Very generic figure here, let's say if this is the landfill, let's say a very generic figure here for now, or let's say if this is the landfill, I am going to have different cells and so on, right. I am going to end up with this particular case, let's say, and let's say I cap it, let's say. So now the waste does not have any access, or has not had any access to oxygen now, right. So obviously anaerobic conditions would predominate, and you are going to have anaerobic decomposition, and in that context you have, what do we say, acetic acid typically being formed, right, and the acidic conditions prevail. So what happens now, you have this acetic acid in contact with your waste, let's say, right. So let's say if there were any heavy metals, let's say, what would happen to these heavy metals when they come in contact with this acid or acetic acid and such? What would happen now? So in that context, we need some environmental chemistry background. What is that about? We know that typically at higher pH, let's say, metals precipitate out, typically anyway, let's say, depending on the type of ligand and such. So they are in the solid form or solid phase, let's say. But as the pH comes down, depending upon the type of metal and such, the metals become soluble, let's say. So what happens now, let's say, if in the municipal solid waste, my particular heavy metal is in the form of a solid initially, and let's say my leachate, so I have my solid here, metal, and now leachate is formed acetic acid, and that starts flowing down, let's say, and now my leachate comes in contact with this solid now, right. So what happens in that particular context here, right? What happens now, as we know from our environmental chemistry background, typically anyway, as you decrease the particular pH, let's say, of that particular solution, your equilibrium shifts, and the solid phase, what do we say, or the heavy metal would be in the aqueous phase and not in the solid phase, right. So obviously what does that mean? It means that your heavy metal, which was solid and immobile, let's say, is now in the aqueous phase and more mobile. So for example, now this leachate, after coming in contact with this solid or the solid phase of the heavy metal, will now have greater concentrations of heavy metal, let's say, and that can contaminate your groundwater. For example, if this is your groundwater flow direction, let's say, and if your leachate collection systems and so on failed, or you did not have any particular leachate collection system, let's say, and now you are going to have contaminated groundwater, right. So this is the worst case scenario that TCLP test tries to replicate, let's say, right. So what are we trying to do? We would replicate the worst possible conditions that you would come across in a municipal solid waste landfill, let's say, right. So in that context, obviously, I think we have the relevant aspects here. So TCLP test. So what is that about? There are 2-3 aspects that we need to consider here. Obviously, leachate, right. So how is that, what's that particular leachate in the municipal solid waste landfill? Typically acetic acid after anaerobic digestion. So again here too we consider acetic acid, okay, acetic acid, that's one aspect, right. What else now? If the solid size is much bigger, let us say, compared to this particular case, and leachate is in contact, let us say, and I have multiple such smaller pieces, in which case would I have greater dissolution of the particular solid or transfer of the relevant heavy metal from the solid phase to the aqueous phase? In the latter case, where I have more surface area, right. So, the other condition that the TCLP or case that TCLP tries to replicate is the particle size, right, particle size. So, typically less than 9 mm size is what the TCLP test prescribes. So, if your particular waste the particles have a size greater than 9 mm, you need to crush them to a size less than 9 mm, right. Again, we are trying to replicate the worst possible condition, right. So, and then again we have equilibrium conditions. So, equilibrium conditions. So, equilibrium in municipal solid waste can be achieved over the course of few months or years and so on, let us say, but here we are trying to, we obviously do not have the time to what do we say, wait for a few years or such. So, here we look at accelerated tests or such. So, obviously what are we looking at? We are going to look at a particular case of where the solid or your particular waste which you are testing and your leachate replicate here, which is the acetic acid combination of liquid which we are going to look at. They are going to be in contact, and this particular tumbler is mixed end over end, right, end over end for 18 hours, right. So, and here what are we trying to replicate? We are trying to replicate the conditions for equilibrium. So, again generic aspects. So, acetic acid, why do we choose acetic acid? Because that is what we expect to be formed in your particular municipal waste landfill. Particle size, smaller particle size, why do we need to look at that? Obviously, because the lesser the particle size, the greater the surface area, and thus the greater the chance of, not chance I guess, the greater the kinetics of what is it now, changing phase from solid phase to the aqueous phase. Again, it is diffusion control typically, right. And again equilibrium conditions replicated by end over end mixing for 18 hours. So, let us move ahead. Again, what are we looking at? Test methods. Where do we find this particular test? In the test methods for evaluation of solid waste, and as we looked at it earlier, it is called the test method or it is 1311, right. And what do we have? We need to consider the solid size. The solid size should be less than 9 mm before you start the test. If it is not, you need to crush it, right. And then you need to have your particular liquid phase and solid phase. Again, to replicate the worst possible conditions, you are going to have 20 ml of your particular liquid to 1 gram of your particular solid, let us say. As in this particular container, you need to have the compounds, not compounds, pardon me, the relevant leachate or extraction fluid, I guess, in the ratio of 20 ml of extraction fluid per 1 gram of your particular solid or waste that you are trying to look at, I guess. So, what am I going to do? I guess in these proportions I am going to put in that extraction fluid or that particular liquid in the mixer, and also the proportionate amount of your particular waste, and I am going to mix that end over end continuously, let us say for around not around, for 20 hours or 24 hours I believe, right. And after that I am going to, let us say, look at the particular concentrations of those particular listed compounds anyway in that particular leachate or the extraction fluid. And what is it that I am trying to replicate? Obviously, so I am going to presume that any contaminant in that particular solid phase or adsorbed onto that solid, let us say, would now change phase into the aqueous or into the extraction fluid now, right. So, any compound or contaminant that was in either the solid phase or adsorbed onto the solid, let us say, we are now going to presume that it is now in the leachate or the extraction fluid. So, once I analyze that particular extraction fluid for those particular heavy metals, let us say, or different other compounds, and if that particular concentration is greater than the particular threshold given in our particular table here, as we have, let us say, for example, let us say I have different compounds here. Let us look at a few examples. So, let us say I am analyzing for arsenic, let us say, and let us say my concentration of arsenic in the extraction fluid end up being greater than 5 milligram per liter, let us say, right, after the TCLP test obviously. Then what do I need to do? Obviously, I need to classify that particular waste upon which I conducted the TCLP test to be a hazardous waste. And then once you classify waste as hazardous waste, there it is obviously a different ball game, and you have different other aspects that you need to look at. Again, in this context, we also need to choose the kind of extraction fluid, right. There you can't just choose acetic acid as in what concentration and so on, and for what kinds of compounds, for volatile and non-volatile compounds and so on. So we are going to look at that in greater detail, but since I am out of time, we are going to wrap up today's session and move on to what do we say, the relevant aspects in the next session, I guess. So again, as we wrap up, what have we looked at? We looked at the stochastic and deterministic approaches. We were done with that, right? And then we moved on to again looking at the relevant law and the relevant aspects in greater detail. In that context, we need to obviously understand whether a particular waste is hazardous waste or not. Why is that? Because if it's hazardous waste, then you have a different set of laws and regulations that deal with its handling, transport and disposal and so on, right? And how do I go about, getting to this particular what do we say case, let's say, of deciding whether it's or a waste can be classified as a hazardous waste? I am going to conduct the TCLP test. And what does the TCLP test do? It tries to replicate the worst case scenario of the waste ending up in a municipal landfill and coming in contact with the relevant leachate or acidified leachate, I guess, right? So thus we have an extraction fluid of 20 ml to a solid of 1 gram ratio, and then put in a particular end over end mixer, and then equilibrium conditions replicated. End over end mixer, why do we have end over end mixing? We are trying to create turbulent conditions so that the particular kinetics of diffusion from the solid phase into the extraction fluid or the particular liquid here or leachate are going to be higher, and we assume that the equilibrium is going to be reached, I guess, right? So here the TCLP test tries to again replicate what would happen or what would be the worst case scenario in the municipal solid waste landfill, and then you are going to analyze for the particular compounds in that particular extraction fluid, and if the concentrations are greater than the thresholds, you would then classify it as hazardous waste. If not, you would obviously not consider that to be hazardous waste, I guess, right? So I guess with that, I am done for today, and thank you.